Would you cross a bridge designed to collapse at exactly the heaviest load it might ever see? Of course not. We design it to be much stronger than it needs to be. How much stronger? That margin is called the factor of safety. Welcome back to Solid Mechanics. Today, factor of safety, working stress, and the simple reason structures stay standing. Let's draw it out. Every material has a stress at which it fails. We never let our part reach it, instead, we work at a much lower stress. The factor of safety is just the ratio between the two. Factor of safety equals failure stress divided by working stress. So a factor of safety of 4 means the material is 4 times stronger than the stress we actually allow. That stress we allow is called the working stress, also known as the permissible or allowable stress. Rearrange the formula, and the working stress equals the failure stress divided by the factor of safety. The golden design rule is simple. The actual stress in the part must always stay below the working stress. So why not just design right at the failure stress? Because the real world is full of uncertainty. The material may be weaker than the textbook says, the load may be larger than expected, a sudden overload or an impact. There are manufacturing flaws, corrosion and wear over the years, and assumptions our formulas quietly make. And where failure could cost lives, like a bridge or a lift, we want an even bigger cushion. The factor of safety absorbs all of that. Now, which failure stress do we divide by? It depends on the material. A ductile material, like mild steel, yields before it breaks. So failure means yielding. For ductile materials, the factor of safety is based on the yield stress. A brittle material like cast iron or concrete snaps with almost no warning. For brittle materials, it is based on the ultimate stress. Ductile, yield, brittle, ultimate. Remember that? How big is the factor of safety in practice? For steel, under steady loads, it is about 1.5 to 2. For brittle materials like cast iron, more like 3 to 4. Timber and concrete, higher still. And for fatigue, impact, or anything where life is at stake, higher again. The riskier and the less certain, the bigger the number. Let's design something. A tie rod must carry 50 kilonewtons. The material's ultimate stress is 400 Newton per square millimeter, and we will use a factor of safety of 4. First, the working stress. 400 divided by 4 is 100 Newton per square millimeter. Then the required area, load over working stress, 50,000 over 100 is 500 square millimeters. Notice we designed using the working stress, never the ultimate. That is the whole point. So should we just make the factor of safety huge to be extra safe? No. A high factor of safety means a heavier, bulkier, more expensive part. A low one is light and cheap but risky. Good design walks the line, the lowest factor of safety that is still safe, and one quick term. The margin of safety is simply the factor of safety minus 1. In one breath, factor of safety equals failure stress over working stress. Working stress equals failure stress over the factor of safety. Ductile materials use the yield stress. Brittle materials use the ultimate. It exists to cover overloads, weak material corrosion, and the cost of failure. And it is always a balance between safety and economy. And that is the factor of safety. This subject is a free package, the lecture, an MCQ practice paper, and a full solution video every day, a brand new subject. All the free notes and PDFs are on our Telegram. Learn Civil Easy, subscribe, tap the bell, and I will see you in the next class. Take care.